Swayam Prabha. Digital India. Educated India.
So that we don't lose the momentum, right? So quickly I will tell, this E is nothing but electrode potential. Electrode potential, what is that? Cell potential. Suppose you have two electrodes, we normally call as anode and cathode, or some people call right hand side, left hand side. So electrode potential here is E RHS minus E LHS. In the second part it will be there. When I give the second part, I would do that. So this E refers to electrode potential at a given temperature and given concentration of the reactants. So this E is electrode potential. In the second part, I think I will be doing it again. So electromagnetism. Normally when we electrochemists do, they don't worry about the magnetic part, like the Gauss electrostatics and all. We only worry about how the cell construction behaves, what the potential, we say 1.3 volt, 1.4 volt, 220 volt and so on. So this E is nothing but electrode potential. F is Faraday, 96,500 coulombs per mole. N is number of electrons that is transferred in the overall reactions, right? There is anode reaction, cathode reaction, together will be the total potential. So that will be coming here, right? Okay. Then when we say G gives free energy, there are what is known as the standard states. For solid, whenever we say pure solid, there is a value G0. Similarly, as gases, there is separate standard state. Advantage is, when you get delta G, when you want to go to G, you need some convention. So they are deliberately taken G for solid 298 Kelvin is 0, G for this compound is 0, like that. So once you define standard states, you can get from delta G, G for any other compound. Because already you have got a convention, G of this substance is 0, like that, and this condition. So you can get from delta G, G itself experimentally. Sir, I don't want experiment means you can get theoretically G from statistical mechanics. That's amazing power of the theoretical chemistry. So whatever you are doing experimentally, within a few minutes we can give you the estimate theoretically. Nowadays when research scholars are doing all the experiments, the journals will ask them to show theoretical calculation to justify this number. So today it has become important for every chemist to have theoretical chemistry knowledge, especially computational knowledge. So today we depend very much on the computer programming to advance further in our experimental research. So that's a very important thing, right? So if you ask one quick application, I can tell you, when you have a diagram where we plot Gibbs free energy change as a temperature, all this will be telling you how to combine these lines to make a reaction occur. That means what? Your overall delta G naught should be negative. So what is 0? Standard free energy change. What is F? Formation. Gibbs free energy change in formation of these oxides as a temperature. Sir, why are you giving this now? Because we can now tell a reaction will it occur at 1000 Kelvin when you have these combinations of oxides. I will go to the next slide and show that. So this is known as Ellingham diagram, known more than hundreds of years ago. Right? This they have done for oxide You can also do for sulfides and so on. This is called Ellingham diagrams. Right? Very important for our metallurgy students. Right? So you can see here, if you want a metal oxide to be reduced to M, RO should be more stable. That means what? You go to the diagram, you have to see between these two which has more negative delta GF, that will be stable. So whenever you find the most negative grip energy of formation, that reaction will occur. Right? That is the power of the grip energy. That's why in the beginning I said chemists are obsessed with Gibbs free energy, mainly because it is going to tell us whether a reaction will occur or not. So our chemists normally call it as thermodynamic feasibility of a reaction is given by delta G. Right? So you can see here, if the position is lower, its stability is higher. Why? More negative delta G we have to see. Right? Then one more example I have given here. Suppose you want to ask whether find the temperature below which the metal M1 will reduce M2O. You are given these two temperature dependence. So you manipulate these two, you will know. That means below 2000 Kelvin, the metal M1 will reduce M2O. You can take down this so that you can work carefully and see. Right? Or you can take photo and see later on. Very typical question for our BTech students and so on, where they should know how to manipulate two chemical reactions and get at what temperature, range of temperature, a particular reaction. What is this number? This is the equation for delta G as a function of temperature. 300 Kelvin, you put T equal to 300. If it is 1000 Kelvin, you put 1000, area 1000. Then see, combine these two algebraically and find out, that's all. Yes. And second one? Yes. This is M2, correct. This is M2 solid plus half O2, very good, correct. So this will be M2 solid plus half O2 M2O. The M1 solid plus half O2. Because this typing, when I normally send to the professional people to prepare PowerPoint due to I have no time. So when they do, they make mistakes. I am not able to see again. So that's the reason this is M2 only. So translate this M2, then correct this and then manipulate, you will get this. Then you find out that the whole delta G should be negative. That will happen when T less than 2000 Kelvin. So you can use any temperature lower than 2000 Kelvin. That is the power of the Gibbs free energy change. Then you ask the question, sir, what are these sudden changes that comes here? Right? Sudden changes that comes here actually are nothing but phase transition, one phase to another phase. Right? That's why it is called the slope change, that is related to the first order, second order phase transition and so on. Right? Then we have the question, will zinc oxide be stable in contact with titanium, for example? The titanium at 1000 Kelvin. These are the two numbers given to you. Right? So, given these two reactions, you form a reaction like this and find out delta G naught. Delta G naught is negative, so the reaction is feasible. So, all you have to do when you find a new compound or new reaction is see whether delta G is negative or positive. Delta G negative means thermodynamically the reaction will occur. Sir, why are you telling thermodynamically it will occur? Because kinetically the reaction may happen after 10 years. Thermodynamics only tells you it will occur. It is not telling you when it will occur. Thermodynamics is going to tell you your reasoning is correct, this reaction will occur. But it is not telling you will it occur in 1 minute or 10 years, it is not telling. That is told only by kinetics. Right? So that's why I always keep on telling thermodynamic feasibility only thermodynamics is telling, but not kinetically feasible. right? So again you can see here how to write the reaction. This is the what I called as affinity in the beginning. These are stoichiometric numbers. All this will be available to you, so you can again and again see this. Long back I wrote a book with Professor Kalidas, who was the head of the department here even before I joined, but he was teaching these subjects. So when I joined, we both wrote this book at that time. It deals with non-equilibrium thermodynamics. This book, a very lucid book, right? A level of +2 should be adequate to follow this book. It is not doing anything bigger than the law +2 expertise. Okay, what I will do now, I will go to the second part, which is equally important. Can you open the other file? Well, let him come. Till then we can go to next. We can call him, you can open the second part, right? Then in between we will see this chemical, electrochemical potential. Right? Chemical potential, ith component is written as a standard part and partial pressure of the ith species. Right? You have 1 minute, I'll finish, then you can go to second. You can open now, don't reopen. Second part you can open, I'll tell in words. So, chemical potential of ith species written as a standard part and non-standard part. Non-standard part will contain partial pressures of the gas. When the pressure is unity, Ln1 is 0. So you get the standard chemical potential. That means what? Standard chemical potential of a compound is the chemical potential at a pressure of 1 atmosphere. Because log 1 is 0, standard chemical potential is nothing but the chemical potential at a pressure of 1 atmosphere. Right? Same way we can do for solid, liquid, gas, liquid, everything. Right? Then what interestingly happens in the chemical potential is the following. You have what is known as a activity of the electrolytes. Right? Suppose I have 1 molar potassium chloride solution. Then we ask the question, sir, you took 1 molar concentration, how much of this 1 molar KCl is actually going to do the work that we are concerned with? Then for that people have got a concept called activity coefficient. There is a relation between activity and concentration through activity coefficient. Right? Very amazing. If you see here, we have activity coefficient given like this. Suppose you have activity of a substance equal to, let us say, activity coefficient into concentration. What is this? We are relating activity of, let us say, sodium ion to concentrate sodium ion. Let us say I'll put sodium ion here. Then I'll put here gamma sodium ion. This activity of sodium ion. So what you are trying to convey? What I am trying to convey is the following. When you have very dilute solution, this gamma will be approximately 1. So your concentration is enough to describe a process. When you go to concentrated solution, you need to calculate what is known as activity coefficient. Right? It is activity coefficient. That means what? Although you might have taken 1 molar sodium chloride or potassium chloride solution, it is not actually involved itself in the process themselves. For that, you should compute this activity. How do I compute? Only if I know activity coefficient. How do I calculate this? There is a differential theory, which is a common thing in electrochemistry. In 1930, it was known. So, we can theoretically estimate this. We can also get experimentally this quantity. So, you use this quantity, then you will know activity. Sir, why you are now telling this? Because your mu, strictly speaking, should contain activity rather than concentration. Fugacity rather than pressure. We wrote PI, that PI itself is not correct. You should know fugacity, which has fugacity coefficient. In liquids, you should put solution concentration, that is again related to activity. So, you see how chemists have thought of all these things. Whatever we are studying today is nearly 100 years old. We are still not able to throw it away. Even today, all that the pioneers have done are very useful to us. That's the amazing part. That means we are still building on what they did. Right? We are still not come far away from this. Right? So, before I go to part 2, let us see any question on part 1. Yes. Any question till now you can ask. Anything not clear? Yes. Feel free.
What exactly is fugacities?
Fugacity is similar to this. Here I wrote activity of the liquid, right? Here it will be fugacity coefficient. Here will be fugacity coefficient and pressure of the gas. So, just like in the liquid and electrolytes, the name is given as activity coefficient. For gaseous systems, it is given as the fugacity coefficient. Any doubt, feel free to ask, don't hesitate. It's your, you come all the way to really learn something. So, if there are no questions, I will go to the part 2. Part 2 is my favorite thing, electrochemistry. My own PhD was in electrochemistry subject in 80s, mid 80s in IIT Bangalore, right? My PhD was in what you can now tell us theoretical electrochemistry. Essentially, I didn't do experiment in my PhD, but now I am doing only experiment and not doing any theory. Little bit only theory, not much, right? So, I would spend the remaining part on showing how fascinating electrochemistry is. So, my objective in the second part is to show the fascinating opportunities that exist in the field of electrochemistry. Right? Today, when you walk everywhere, you see battery powered vehicle, electric vehicle, e-mobility, and so on. All of them rely on electrochemical principles. Today, electrochemists are in great demand everywhere because they are the ones who can tell whether a system will work or not. So, electrochemistry has become extremely important today. Today, when you see any journal, there will be at least 10% of electrochemistry in the journal, even if it is organic chemistry or inorganic chemistry work. Because the journals will ask, where is electrochemical measurement? What measurement does the people do? They measure electrode potential. When you measure electrode potential, you will get delta G. So, for everyone today, measuring electrode potentials are important. That's why today journals insist on electrochemical measurement. So, in the beginning I said the difference between these two are, here it was chemical potential, here it is electrochemical potential. Right? Sir, what's the difference? If you have a charged species, you will have electrochemical potential. If you have a neutral species, you will have chemical potential. Again, remember the activity coefficient, everything will come here also. Then electrochemists have divided electrochemical cells into two types. What are the two types? Galvanic cell and electrolytic cell. What's a galvanic cell? You get energy out of that cell as a result of electrochemical reactions. As a result of electrochemical processes, you get energy out of that. Such cells are called galvanic cells. That means you are getting energy as a result of electrochemical reaction. Right? What is electrolytic cell? You apply energy to make a reaction occurring. That means you are applying electricity or electrode potential to bring about a chemical reaction. That is called electrolytic cell. So electrolysis. That means you electrolyze a electrolyte so that you will get a product. For that you supply energy. So it is electrolytic cells. In a galvanic cell, you get energy out of the cell. Here you are supplying energy to make a reaction, get a product. Electrolysis of water will give H2 and O2. So you electrolyze water, you will get hydrogen and oxygen. You combine hydrogen and oxygen, you get water, then become fuel cell. It's a galvanic cell. That means even hydrogen and oxygen you can do two things. You can electrolyze water to get H2 and O2, or you can use H2 and O2 in a particular manner to get energy out of it. Right? So that is a galvanic cell. Driving force is applied potential or applied field. Then electrochemists have divided their field into three topics for convenience. What are they? Ionics. Ionic means movement of ions in solution. Movement of ions, sodium ion, chloride ion, bromide ion, lithium ion, all of them moving in the solution are known as ionics. Ions migrate towards electrodes, right? When you dissolve NaCl in water, Na plus Cl minus comes, right? So there is a dissociation of the electrolyte into ions. These ions migrate. So that field is called ionics. Ionics refers to the study of ion migration in electric field. Right? So that is ion migration. Then what is electrodics? A process that occurs at electrodes. A reaction is occurring at electrode, that is called electrodics or electrode kinetics. Right? A molecule far away from the solution will come towards the electrode surface and undergo a reaction. It becomes electrodics. That field becomes electrodics. In ionics, ions are moving in electrolyte solution. We want to know how they behave. So it is ionics. Here, a reaction occurs at electrodes. So it is electrodics or electrode kinetics. Then interfaces. Whenever, suppose I dip a metal electrode in a beaker containing the electrolyte, there will be interface that is formed near the electrode surface, where the water molecule, let us say, will come towards the surface and water will be present on the surface. That field where there is interface between electrode and the electrolyte is called interface. Electrode-electrolyte interface, or normally we call it as a electrical double layer. Two layers of charge are existing, one near the surface, one near the electrolyte. So interfaces is a broad topic in electrochemistry. My own PhD thesis was on the interfaces. I did work on the statistical mechanical modeling of electrode-electrolyte interfaces. Interface is, suppose we have, let us say I have a beaker where I dip the electrode. Let us say I have a beaker here, let us say. Then I have a platinum electrode, let us say. Platinum electrode. These are all electrolytes. Let us say sodium chloride. Example. Right? So when I dip an electrode in the electrolyte solution, right, this Na is going to be Na plus and Cl minus. Right? And always there is a water molecule present. So the Na plus will come and very near it will come here when you apply the potential. When Cl minus can come very much near the potential depending upon the potential you applied in the system. Similarly, always water molecule will be surrounding this electrode. we call it as a solvated electrode. Water molecule will be surrounding the electrode that I took. The study of how the ions and molecules behave at the interface is the interfacial electrochemistry. So answer to your question is, the study concerning the behavior of ions and molecules on the electrode surface when you apply a potential is the interfacial electrochemistry. Yes.
How is it different from the electrode?
No, here we are only looking at the, very good question. Here we are only looking at the organization of molecules. Organization. For example, how much Na plus has come here I want to know. I am not interested in knowing whether this Na plus became Na or the Cl minus became chlorine. I am not interested there. I am only interested in how much Na plus has come to my electrode surface after I applied 1 volt of potential. How much Cl minus came here when I applied the potential some amount. I am interested in knowing how much ions or molecules got absorbed on the electrode surface. I am not asking the reaction between Na plus and the platinum. I am not asking the reaction between Cl minus and platinum. I am not asking whether the water became electrolyzed. So the difference is, it's a very important question. Electrochemists have two terminology. One is called polarizable interface, one is called non-polarizable interface. When you are studying these type of interfaces, we apply such a potential that reaction will not occur. So that our aim will be only focused on seeing the molecules here, how they behave. That's all. Then you may ask, sir, why should we know? If you are not going to do any reaction here, then why are you interested in this? After all, only let 1,000 molecules come or 10,000 molecules come. Why do I worry? I worry because this has a bearing on the efficiency of the reaction later on. When you carry out a reaction, if water molecule are totally covered here, then electrode will not be available for the reaction. So I am losing that. Yes.
Sir, when the redox reactions occur, there's a diffusion layer that's formed around the electrode, right? Would that come under electrodics or interfaces?
Excellent question. Excellent question. See, in the next slide is there. Quickly I will tell that. See, this interface that we are talking of the double layer is of the 3 to 4 or 5 angstrom thickness, whereas the diffusion layer is much larger than that. So the diffusion layer where the reaction occurs is spanning a big region of 10 or 15, 20 angstrom. It can even be even more by applying some potential and rotating the electrode. Whereas this organization that occurs here is of the order of 3 angstrom. Sir, why it is 3, why not 20, why not 40? Because it is the thickness of water molecule that dictates. So it will be roughly of the order of 2 to 3 angstrom something. So I will draw that picture. This is the way we tell the electrode. Right? This is my interface. This is the bulk. Bulk means my solution. Right? Suppose I have here Na plus, Cl minus, all these things, lithium ion, sodium, bromine, let us say something. Then here these ions will come here, right, and stay there for some time. Similarly, this ion will come there and stay there for some time. Then this water molecule will always be present here. Water. Right? So the answer is the ions or it need not be, it can even be neutral molecule, methanol, formic acid, and so on. So they can come by diffusion here. In fact, they will come by diffusion here, right, and then stay there. But when we are studying the interfaces, we are not worried about the diffusion process. We are rather worried about how these molecules are present. What is the coverage of these molecules on the electrode surface? If lot of water molecules are covered here, what will happen to me? The electrode is not available to carry out my fuel cell reaction or battery reaction. So even to know, I must know how much has been present here, how to eliminate them, how to minimize them. So the study of interfaces is nothing but adsorption of ions and molecules on the electrode surface. Right? So to your question, this is the thing. Interfaces are essentially the organization of the ions and molecules. Right, that's all. So if we study only that, it becomes electrical double layer theories, which was my own PhD topic at that time. Right? Then when we want to study corrosion inhibition, for example, we need to know how much of the electrode is covered with other unwanted substances. That's why they become important. Suppose you want to prevent corrosion of a metal, then if a molecule gets adsorbed, it is good for you, because metal won't get corroded. You have prevented the corrosion by inhibitor. So you will add an inhibitor to the ion, let us say. So the inhibitor will get adsorbed so that your ion won't get corroded. Right? So there are occasions when the adsorption is good for us. So you can add an inhibitor to prevent corrosion of metals. That's a whole field called corrosion inhibitor. Lot of theses you will see in 1960s, 70s, 80s, they only study corrosion inhibition. Take a system, keep on adding, let us say potassium chromate, chromic acid, something. Any substance you add, it will get adsorbed on the electron and prevent corrosion. You study how much corrosion prevention, your topic is over. Like that. So 1960s, 70s, this is what they were doing. Take a system, add an inhibitor, study the corrosion inhibition, that's all. But now they are outdated, much sophisticated things. Any other doubt? So interface is different, it's different. And the migration and diffusion will come shortly. It is there, a slide is there for that. Electrochemistry is nothing but electricity and the chemistry, essentially. Right? Now you see here historically, first time the water electrode done was on 1800. Right? Then in the ionics, there is a Groth's conduction mechanism. Right? We will find that H plus has the highest ionic conductivity among all ions because of its size and the mechanism. That was in 1807. Even now, MSc students have a topic in the Groth's mechanism. There will be a question on this field for even MSc students. Then 1824, Davy did corrosion prevention studies. Then everything we study is due to Michael Faraday. Faraday's laws of electrolysis, Faraday constant, all in 1833. Then 1874, Kohlrausch law came, ionic migration. That means he said cationic conductivity plus anionic conductivity, nothing but total conductive electrolytes. So if you sum the ionic conductivities of cations separately with anions, you will get the total electrolytic conductivity. At that time it is a big thing. Then Arrhenius came in 1887, he gave theory of dissociation. Weak electrolyte, strong electrolyte, all of them names given by Arrhenius. Then Nernst came 1889, Nernst equation, which gives electrode potential. How you write electrode potential for a given reaction is given by Nernst. Mn plus n electron giving M. Then the way you write E equal to E naught minus all these things is due to Nernst. This E naught is standard electrode potential. This is a Nernst equation. So this is a contribution of the Nernst. Then 1902, Cottrell came with the equations for diffusions. Cottrell equation, very famous. Then 1905 TOEFL, very important. The only name we should never forget in electrochemistry is this TOEFL equation. Yeah, I used to tell my MSc students, anything you can forget in the exam except this. Because without TOEFL equation, no energy storage device can be built. Because the TOEFL equations only are going to give the way anodic current is going to change, the way cathodic current is going to change, where the total current is going to come, where the efficiency of the process. So, the TOEFL equations, I will write after a few minutes, the TOEFL equation. What does TOEFL equation tell? It gives the relation between current and potential for any electrochemical reaction. That's all. TOEFL equation is nothing but a relation governing current and applied potential. That means when you want to devise a new battery, you would like to know what is the efficiency, how much current I can get, how much power I can get, how much energy I can get. So, for that you should know, if I apply 1.3 volt or 1.5 volt, what will be the current? It becomes what is known as the current efficiency. Right? So, that is solely due to TOEFL. That's why the only name we should never forget is TOEFL. Extremely important. Then when you come to this Swarovski, Nobel Prize in Chemistry in 1959 he got. What is so special that he deserved Nobel Prize? Because before he came, the general thought was electrochemical reactions, right, can never be reproduced. Today you get a result, tomorrow you get some other result, day after tomorrow result comes. So electrochemical data people believed are never accurate enough for any purpose. Then Swarovski came and said that no, it is not like that. If you take a mercury electrode, which he called a dropping mercury electrode, and carry out a reaction, what he called as polarography, then what it does is, for every ion, there is a characteristic potential called half-wave potential, half-wave potential, E half, then which is related to E naught. This is called as the half-wave potential. What is that? Suppose you take 10 ions and give me the polarigram. Actually, we have an experiment in MSc, now we have removed it, we are doing it about 10 years back. What it does is, if we have, yourself, you listen here. If we have an electrolyte, if you have a beaker where you have given me 10 electrolytes without telling their names, I will run a polarigram and tell you what is that ion, how much is present. That is the power of the Swarovski's invention. That means you give me a system without telling me how much is present and what is present, I will run a polarigram. The experiment is called polarigram or polarography. Right? So, he can use it for qualitative and quantitative analysis. Sir, then why others didn't get before him Nobel Prize? Because others were using solid electrodes, platinum, silver, gold, nickel, and so on. Swarovski's invention, big breakthrough was used a dropping mercury electrode. Advantage is every time you get a fresh mercury drop, so result becomes reproducible. Whether you do the reaction in here or in CLRI, the same result will come. Sir, why can't it happen in platinum electrode? Because it depends on purifying the electrode every time. You do one experiment with platinum electrode, it gets impure. You have to again clean the electrode and do it. Your cleaning of the electrode will be different what CLRI person does. So the results become irreproducible. Where dropping mercury happens, mercury will come from reservoir. Then you will have a connection with potentiometer, all these things. So every time you get a pure surface. So results have to be reproducible. Whether you do this work here or in South America, same result will come. because your electrode need not be cleaned every time. In our MSc lab, if Prasad is there, he will show you the setup. There will be a reservoir, from there mercury drop will come. There the reactant like sodium ion or potassium ion or something will come and undergo a reaction on the mercury electrode. Then we draw what is known as the polarigram. Right, I will do that. It is called a polarigram. It's very important because it's a Nobel Prize discovery, so we cannot ignore it. Right. Suppose what he will do is, he will measure current here and potential which applied. Then it will go like this, approximately from here, it will go like this. Right? Let us say, these are typical, this is called polarigram. What's a polarigram? A current between current and potential on a dropping mercury electrode. Then, right, the place where the current is I by 2 is called halfway potential. So, this E half is called as halfway potential, where the current is half of the maximum current, I by 2. Very interestingly, this E half is characteristic of a particular ion. So, if somebody says, sir, E half is minus 0.3 volt versus a standard hydrogen electrode, I will tell you this is the ion present. That means somebody gives me this polarigram, right? I will be able to tell this is the ion present simply by looking at this number. Then, how do I tell the amount that is present? Amount that is present is given by this magnitude. This is known as limiting current. This limiting current will tell me the amount of ion present. This potential will tell me the nature of the ion present specifically. So, using this program, I can do both qualitative and quantitative analysis. So, Nobel Prize has to be given to you. That is the power of the Hierarchy invention. Hierarchy also has come to India a few times those days. Hierarchy students I have met in ISC Bangalore is very fond of India very much. Right? So, this is a very important thing. I took it from a particular book which is already on internet. I took this development from this book only, right? And I put a dotted line because many I have missed here. Because all if I start writing, I cannot do further. So I left very important names, right? To me, TOEFL very important. Hierarchy because of that. Can anyone name other Nobel laureate in electrochemistry apart from hierarchy? Any other Nobel laureate who got Nobel Prize? Electrochemist, roughly electrochemist. Anyone can tell the name of any other, at least one electrochemist name? Many may be there. I am telling one name, can you tell who got Nobel Prize for electrochemistry after hierarchy recently? I think it will come in on one of the slides. Next slide also it will come. Right? See, this was an electric car somewhere in 1899. It ran for 1 kilometer with the speed of 105.9 kilometer per hour. Right? Then why this became very obsolete after that sometime? Because very costly. The electrodes were platinum essentially. So people throw away this invention once and for all. Right? Then I will spend 5 minutes on this. What are various facets of electrochemistry? Electro-organic chemistry. That means today you can synthesize many organic compounds only by electrochemical route. There is no other route available to synthesize some organic compounds except by electro-organic route. Specifically, if you want a stereo-specific product, it's possible. Right? Then energy storage devices, batteries, fuel cells, supercapacitor, or IIT Madras, the thrust area. We got huge amount of money from the government of India for the energy storage devices. Then corrosion of metals, prevention of corrosion. Then conducting polymer. Our lab, we did lot of work on polypyrrole, polyaniline, polythiophene, polyindole, and used it for supercapacitor and so on, and biosensors. We used this. Then nanometal you can get by electrochemical method. Medicinal chemistry, our department has a huge program on medicinal chemistry. We got huge amount of funding from industries to carry out the work in medicinal chemistry. Then biosensors, glucose sensor, urea, dopamine, and many other things, nicotine, many things. Our lab was doing a lot of work on this. Then titrations, conductometric titration, potentiometric titration, impedimetric titration, so on. Very important. See, that's why no one can claim I am electrochemist. Why they cannot claim all this? Nobody would know. A small topic within one of these somebody may know. Electrochemistry is so wide, so no one will be able to tell authoritatively on all these things. We can say I know a little bit of electrochemistry, we can tell. In this conducting polymer, I can tell. I can tell I know a little bit of double layer theory, I can tell. I can tell I know a little bit of corrosion, I can tell. It's a very wide area. Today, textbook electrochemistry are hundreds. If you go to internet, daily one electrochemistry book is coming. Right? So, you will see the electrosynthesis thing, right? How much is magnesium put electrochemically on this? This is less important, right? That's the corrosion, right? This I want to show you. One name I can tell is this. Rudy Marcus got Nobel Prize for electrokinetics and chemical kinetics. Rudy Marcus got in 1992. I met Marcus once in Germany when I was going to IIT Madras sent me for a conference in Nobel laureates in Lindau from 2004 or something. I went at that time, only Nobel laureates were there in the conference, nobody else. Our institute sent one participant, which is myself, but other people from other parts of India came. Now it's an annual program where our government is sending some 20 students every year to conference on Nobel laureates. Only Nobel laureates will be there to give talk, nobody else. Our government mission is to make students directly interact Nobel laureates and get benefited. Also, you'll get a lot of time to talk to them because entire 3-4 days they will be available to talk to you. They have no other engagement. All the 3-4 days they'll be available, right, throughout in the same venue where all of us will be staying. So it's a government of an initiative where it is sending every year maybe 20-25 students at all levels, MSc, PSc, PhD, and so on. When the first year it started, our institute sent to me at that time. Then Marcus gave a talk. I was talking to him for some time, right? So this is a Nobel Prize in chemistry. Many others also got. I will leave it to you to check. Right? So you see now, in chemical kinetics you ask question on order molecularity. In electrochemical reactions you don't ask this. You ask only current and potential. How much current I obtained when I applied this potential. So to me this is the kinetic data. Here the diffusion, migration, convection all will come. Right. So to me, electrokinetics means depending only current and potential. Here also you can see current and potential. Right. So in electrochemistry, potential driving force. In kinetics, temperature. Right. You apply 1000 Kelvin in chemical kinetics. Here 0.5 volt, enough to drive the reaction. So electrochemical reactions are far more powerful than the temperature applied kinetic data. That's why I keep on telling students, whenever you find a new material, all you have to do is come to our PGP lab or MSc lab, simply make it as an anode, take one cathode, measure the potential and current, you will get everything you want. all molecular property you want, you will get by a measurement costing 100 rupees maybe. That's all. So that's the power of electrochemistry. People should know that. Okay. Then, like I said, galvanic cell and somebody asked reduction oxidation, it is here. Redox reactions. So, redox reactions are occurring. When we do interface, we don't worry much about that. Then you have concept of reference electrodes. Because even to measure a quantity, you need a reference. So, that is called a reference electrode. So, people normally have chosen standard hydrogen reference electrode, which is given as the zero potential at 298 Kelvin and 1 molar sulfuric acid or 1 molar activity of the electrolyte. So, we need a reference electrode to measure the potential. So, that is the concept of reference electrodes. So, the diffusion you have to have come here, you can see here, there is a diffusion component in the overall current. There is a migration component, which is this convection component. Right? So, in electrochemistry, every current is a sum of diffusion, migration and convection. Then electrochemists are very clever. What they do is the following. Electrochemists are so clever, what they do is, sir, if all these three occur, I can never understand a system. So what people do, they avoid convection. How do they avoid convection? They won't rotate the electrode. So electrode will be stationary like this. So convection is avoided. They won't rotate the medium or something, disturb the medium. So convection is avoided. Then to avoid migration, what they will do, they will add what is known as excess supporting electrolytes. What it will do, it will avoid migration of the species you are studying. If you see, I have given NPTEL notes in electrochemistry, they very beautiful, you will enjoy that. There I have said how supporting electrolyte will avoid migration. If you log into NPTEL website, I have given 16 lectures or 20 lectures in NPTEL web course. It's not a video, but you will get all the notes, question, answer, everything you will get. A lot of questions are there with answers. Questions without answer also is there. So, the NPTEL website with Mangal Sundar was doing at that time. Right? So, why I am telling, electricals are so clever that they can avoid migration, they can avoid convection, only diffusion they study. That's why, like she was saying, diffusion layer comes. We are not telling migration layer, we are not telling convection layer, diffusion layer. Because diffusion is the only process. Sir, now is it simple to analyze electrochemistry? No. Only diffusion is there also, it is extremely difficult. Today you take electrochemistry textbook, it will look like a mathematics textbook only. It will only partial differential equation, nothing else. Laplace transform, Fourier transform and so on. Even with diffusion only present, electrochemistry requires excellent knowledge of mathematics. Without that, we cannot comprehend. That's the reason why I skipped the previous slide also. I need some time to discuss that. That's why I skipped. So, even today, with diffusion alone, electrochemistry expertise requires high expertise in mathematical modeling. Right? That is something very important. Right? So, I have no time, so others have to speak. So, I will give you the summary here. What I have done in the second part is the following. What I did was, I told the importance of electrochemical systems, how they are very, very important, both historically and otherwise. Then, in terms of, I didn't tell in the slide, but I can tell now. See, digital signal processing is very important for electronic engineers. Electrochemists also require that. Extraction of metals, very important for metallurgy students. And electrochemistry is very much needed there. Right? Any reactor you want to design, we need chemical engineering. So, chemical engineering is also very important. When you have concrete corrosion, civil engineers become very important. Right? When you want to do mathematical modeling, you need computer science. You see? So, electrochemistry has become highly interdisciplinary today. whether a process physicist or mathematician or chemist or biochemist, everywhere electrochemistry will have a very important role to play. Then little bit of fundamental concepts I told. So with this I will conclude and thank all of you for listening, and any questions you can ask me or send by email whenever you get time. Any yes? Because a very good question, very good question. See, when very excellent question. That's why I like coming and giving talks to young people because of these excellent questions. You see, when ions get diffused and comes to electrode surface, the diffusion current is determined by the diffusion coefficient of the ion, which is normally 10⁻⁻⁵ centimeter square per second. So whatever you do, you cannot increase that current beyond a point for a given electrode. And when the ions come to electrode by diffusion, it is coming at its own pace, because the diffusion coefficient is a fundamental property which we cannot change of that ion. So diffusion has become a inherent property of the ion. So we cannot change diffusion current. That's why in the polarigram, if you see, it will be 3 angstrom, microampere and so on here. So diffusion current cannot go beyond a point, whatever be the system you choose. Whereas I want to increase the current to a very high value, and I want the ions to come very fast to the electrode surface, then I rotate the electrode. I can rotate the electrode 1000 rotations per minute, 10,000 rotations per minute in the instrument. So deliberately I can make the ion to come to the electrode surface much faster. It is useful to me. So if I want an ion to come very quickly to electrode surface, I will do convection. Right? So it is important for me to control the speed of the ion at which the electrode is really reaction is occurring at the electrode surface. So we deliberately can use convection so that we can study how the current is affected due to convection. That's why there's a field called rotating disc electrode. My lab used to have the instrument. Now I have no students. At that time we are rotating, this called rotating disc electrode. Disc geometry very good. So we call rotating disc electrode. Our MSc lab has the instrument even now. So those who want to see, we can tell Prasad to show you the electrode assembly. You can rotate the electrode, rotating disc electrode. So by rotating, you make convection to occur. Like that. Similarly, if you want migration to be studied, you can do something and make supporting electric concentration so that migration also contributes to total current. That's why I said electrochemists are very clever fellows. They can study all the three together or only one of their choice. If you ask for migration, why do we need conductometric titration? Depends on migration. So what we'll do, acid-base titrations we can do by conductometry. Our BTech students used to do experiment on conductometry titration in 1994, 95 and all. Now we have removed them. So obsolete we thought. So what it will do, we'll plot conductivity like our usual titrations. What we'll do, we'll be plotting experimental conductance, which is our molar conductance, and volume of sodium hydroxide added. That means I will take HCl, acid, sodium hydroxide base, I will carry out acid base titration. And my conductometric graph will have something similar to this. This volume will tell me the unknown concentration, right? That's why one of the slides you will find. You can see titrations. So you can have conductometric titrations to see what is the concentration of the unknown solution given to you. Normally the inorganic chemist fellows also do that, but they need an indicator. Here I have no indicator. And this endpoint will come graphically, so you don't need extraordinary precaution near the endpoint. Automatic endpoint will come from graph. You add 5 ml, get this value, 20 ml, get this value, 100 ml, get this value. You draw this graph, you get the endpoint. No indicator is employed. This you can do for redox titrations also. Right. So migration also we cannot say useless. It is useful for analytical chemistry. Convection also very useful. Diffusion is always useful. How do you mean applied potential? The driving force for migration is the potential gradient. That means Ohm's law. That means Ohm's law only, namely, if you apply a potential gradient, that means you apply a potential between the two electrodes, you are bringing the migration. After all, ionic conductivity is what? It is a measure of how the ions respond to electric field. So you apply electrode potential, how much is the conductivity? If you know, you will know how much is the migration effect. That's it. Any other question? Okay, then if there are no other question, feel free, and all the best for you, whatever you do in future. Enjoy the stay and get the maximum out of our institute.
Thank you, sir, for taking time in your busy schedule and coming here to deliver this lecture for us. So through this lecture, we understood how different parts of chemistry are inseparable as you link thermodynamics and electrochemistry here. You also cleared our doubts very patiently. Thank you very much, sir. We are waiting for your next lecture. Also, I'd like to thank the RSIC management and the IIT Madras team for organizing this lecture. Thank you.